So my presentation is going to be rather complementary to the one of Thomas. Okay. So I will focus more on frequentist methods because they are the ones I know better, but not because I'm pro frequentist or instead of being pro Bayesian in the same way as I think Thomas is not pro Bayesian. But simply try to know every method and try to choose the best or the better method in each situation. This is what a good researcher should do, not take a party for ideological principles. So before I jump into the problem of some consideration on frequentist estimation of ABM, I will just advance some very loose consideration on Bayesian versus frequentist approach. I think this can be useful since I believe we are talking to students. So basically you have to opposite approach since Bayesian in a way take that parameters are the random variables. So you have parameters are random distributed variables. So you want to recover the true distribution of these variables, which is the posterior distribution, which Thomas was talking about. And at the opposite end, you have instead in the frequentist approach that parameters are given values, so they're certain in a way. Instead, what is uncertain in a frequentist approach is the data. Why? Because the data are thought to be the outcome of a sampling procedure. So according to the kind of sample that you draw, the features and the statistics of the data will be different. Okay, so what is the main strong point of the Bayesian approach is that you don't have to rely on asymptotic argument, so you don't have to think that your sample is going to infinity to obtain some estimate of the uncertainty of your parameter estimates. So this is the main point that make people choose or opt for Bayesian. At least in my opinion, this is just my personal thoughts on the topic. There are also some drawbacks in my view. For instance, I think a strong point of the frequentist approach is that the design of experience matters, while this is not so true in the Bayesian approach, where the likelihood principle holds. I don't really have the time to go into this, but this is quite basic, so you can find yourself more details on what I'm talking about. But it's just to say that you have some trade-offs between the two approaches, and then you have one other specificity of Bayesians is the use of prior distribution, and Thomas was talking about this. So this is good in a sense that allows to quantify your initial uncertainty, and also, but on the other hand, it can be a source of tweaking. That in the same way as Thomas was talking about macroeconometrics, where you choose tight priors and then in fact you're predetermining the values of your parameters. So of course tweaking is not very good because you don't allow the data to speak for themselves. Okay, so so there again, I'm saying there are trade-offs. So there are pros and cons in principle from these two kind of approaches. So we would like to have the best of both in principle, but unfortunately nobody came up with such a thing. So we need to choose, and usually with a pragmatic attitude, so on a case-by-case basis. So Of course, there is a difference. There are different situations. For instance, when samples are large, so when you have a lot of data, then the problem of the small sample properties of the estimators in the Frequentist framework is less relevant, because you might think that you are close to having an infinitely large sample. So large sample in general are better behaved than the small samples from a frequentist perspective. At the same time, so we might think that large samples tend to favor a frequentist approach. That's why also, as Thomas was explaining, instead macroeconometrics has become more and more reliant on Bayesian estimates, but for the wrong reasons, as he was saying. So, on the other hand, a frequentist approach is valuable, especially when you have simple models, from which you can derive closed forms. Then you can directly maximize some function, and this is much faster than relying on a high number of simulations, like in examples that Thomas made. But of course, we are more interested in complex models. So when we come to deal with complex models, then the advantage of the frequentist approach tend to become more relevant from the point. So the computational advantage of the frequentist approach becomes more relevant, because you need to rely on simulation even in a frequentist frame. So the two approaches get on the same footing, okay, from this point of view. So, okay, so then I'm going to, having said that, then I'm going to go into the main topics of today, which is, in the first place, I will talk a bit about more in general about estimation. So why we should rely on estimation and not on calibration in some specific sense of calibration. And then I will talk a bit about what are some good ingredients when you go to into the issue of analyzing the output of your ABM model. So Thomas was talking about macro ABM model and the hurdles of estimating macro ABM models. Then this underlines the importance of having a good diagnostics of your model in the first place, to work with models whose parameters are well identified in the first place, in order to hope to be able to estimate them. So if you don't do the good work in the modeling step, it's a bit hopeless that you can be able to estimate this model later on. So this is the point of my talk, the main point of my talk. So let's talk a bit about estimation versus calibration. So as we know, one of the, let's say, the most fundamental principle in science is that you should not rely on unobserved entities or variables. So this is well-known Occam's razor. Unfortunately, in economics, models in economics, instead, they come with a lot of unobserved variables. This is because of, okay, there are data limitations, but more than that, it's because economic phenomena are so complex that you would always need further data to fully explain them. So as opposed to the case of physics, I mean, in physics, you have a very, let's say, clear-cut, simple, and beautiful theory, which is Newtonian mechanics, and it works for a number of things. Instead, the simpler and most beautiful and tractable model in economics are simply worthless to understand reality. So, of course, every science faces a trade-off between simplicity and simplification and, say, complexification, better than complication. but in economics, this trade-off is particularly severe, okay, because you cannot do almost nothing with simple models. So a good idea with unobserved variables is to try to get rid of them. Okay, so this is the first meaning of calibration. So try to fix some unobserved variable with the help of evidence, or with the help of empirical evidence. So one textbook example is the elasticity parameter in the Cobb-Douglas aggregate production function. So we know that if labor is paid at its marginal product, so this alpha should be equal to the wage share in the national income. So we can just plug this value into this function, and then try to see if the data on production fit with this functional form. Of course, this is not the case. We know that very well, but this kind of calibration is, in my meaning, calibration in a good sense. Why? Because it constrains the model. So it takes away one degree of freedom from the model, which is alpha, by fixing it on the basis of the evidence, and so making a test of the model with the data more robust and more indicative. This is methodologically good. So this is a good, this is the good meaning of calibration. But what happens if not all the variables, not all the unobserved variables can be calibrated in the first sense of the word? Then the best option is to let yourself be guided by the data. So this means choose the unobserved variables in the best way according to the value that provides the best fit to the empirical evidence. And then you come to estimation. So be it Frequentist or Bayesian, both these approaches provide you with some optimized value and with a formal treatment of uncertainty. This, so estimation in this meaning is simply, let's say, the proper way to proceed, while if we mean by calibration other things like optimizing, but without an assessment of the uncertainty of the value of the parameters that you obtain, or otherwise simply arbitrarily fixing the unobservable variable at will. So these meanings of calibration, okay, are a second meaning of calibration. These are the bad meaning of calibration. Okay, so this kind of approach, this sort of second kind of calibration, is something that we should avoid. And that's why we instead would need to work on proper estimation of agent-based model. So when we come to ABM, we know that we have, of course, a problem with computational resources. We can have a problem with computational resources because our models are complex, and especially if you go to macro model, you have a lot of parameters, a lot of procedures to run. So computation becomes very expensive. So in order to study what is the behavior of your, let's suppose, complex agent-based models, you want to observe some output of the model over a wide range of values of parameters. But the simulation are expensive by hypothesis. So how would we sample the possible values of the parameter in order to achieve two goods? So both having a small number of simulations, so having a small sample of parameters, so parsimoniousness, but at the same time having a representative sample of parameters. So we need to achieve both parsimoniousness and representativeness. So representativeness can be achieved if we use some regularly spaced values. So the problem with this approach is that, of course, if you build a grid of values, this grid will grow to the power of the number of parameters. So this number n to the power of k becomes quickly very too large to be handled. Okay, so at the opposite, you can achieve parsimoniousness by simply fixing the size of the sample of the parameter space that you want to draw, and then draw at random. But this will, in general, not be representative because many points will be, some points will be close to each other, while some regions in the parameter space will be empty. So we can do better with a careful design of experiments. I'm not going. I mean, it's filled with various algorithms, various kinds of approach. I will give you only one example, which is Latin hypercube. So a Latin hypercube simply is in this case we're dealing with a Latin square. So basically each point here represents a draw from a couple of parameters in the range from 0 and 1, and the property that we have on the left is that each point that you see is the only point at the same height and the only point at the same the same point in the vertical axis, and the only point at that point also in the horizontal axis. So there is no superposition of sample points when you go at the margin of the distribution. You see that the difference on the left between this Latin hypercube sample and the uniform sample, and you see it on the margin. So here at the margin, the Latin hypercube samples behaves like a regular grid of values for the single parameter. So this is representative, but we can fix the sample to be much sparser. So this is of course not a regular grid. So these are the same number of points that you have on the right hand, which is a uniform sample, which doesn't guarantee that all the values of the parameters are sampled. Some parameter values are not sampled, and some others are sampled more than one. So although the two graphs in the center part look similar, they're quite different. So a proper design of experiments of your simulation will allow you to achieve a better results on the analysis of the behavior of your ABM. But why do you want to systematically analyze the behavior of your ABM? So we have said that ABM computations are expensive, okay? But the other problem that we have is that we don't have any reduced form for ABM model. So we don't know the shape of the relationship between the inputs, which are the parameters, and the simulated output of the model. So this is completely unknown. So if we have some function, some approximation, some function which links the inputs and the outputs, and plus a suitable set of random variables, we could use this approximation as an avatar, let's say, of the ABM, and so simulate this numerical function and bootstrap the error terms, which would bring a much lower computational cost. Okay. And also this numerical function would also draw a clear relationship between the inputs and the output of the model, so would provide a reduced form from the ABM, which is very useful also for theoretical purposes, so for the theoretical interpretation of the model, especially if you think that, for instance, some exogenous parameter is a policy parameter. So you want to know what is the reaction of, let's say, the GDP to, let's say, raising the interest rate, which in this case would be an exogenous parameter, for instance. So in order to know how your model reacts to this kind of policy instrument, you need to have a reduced form of your model. So in general, an ABM is a function of, so this Y are the endogenous variables, that is the data that is generated by the ABM. So this data is a function of past values of this data from the previous steps of the simulation, of some random variables, okay, so potentially from all the history of the model, and a function of the parameters, okay? And as we have said, F is completely unknown. So since we are not usually interested in the data themselves, but in some function of the data, we can think to argue that maybe it's possible to achieve something that is a relationship between these moments and the parameter plus some error terms, where G now is a known mathematical expression. So does this metamodel exist? We have no guarantee about that. What we can do is try to use statistics to try to see if a good or relatively good metamodel is available for our ABM. Okay, so we can estimate this equation from simulations. So this is an example of this procedure. Of course, you can use different regression equation. You can use different approaches. Here in this case, we are using weight and least square. You can use selection criteria to select among different approaches and different models. In this case, we are lucky enough to get high fitness. So Q square is a sort of R square out of sample. So these models are selected by predicting, by estimating on a section of the simulation and predicting the values on the other section of the simulation. This is called k-fold cross validation. And if we are lucky enough, we see that the simulated moments and the predicted moments are very close to each other. This is simply the average growth of industrial production in a simple ABM model that we have in this publication that will be referenced at the end of the presentation. And we see that there is a very big alignment between the approximation, which is obtained from the metamodel, and so this is the prediction basically of the regression which is the metamodel, and the simulated moments. Okay, so but in other cases the alignment is not perfect. You see that here we have a good agreement for intermediate values of the variance. This is the variance of the industrial production, and less agreement with extreme values. Also, you see there is a lot of uncertainty. So these small circles here depict the different outcomes of simulation with the same parameter values, but different random seeds. So you see there is a lot of uncertainty in the outcomes, okay, depending not on the value of the parameters, but depending on the randomness of the model. So this, of course, brings with itself a potential identification problem, because it means that the output of your ABM do not depend strongly from the values of your parameters, but more from random noise. Okay, of course, this is not a good thing for identification. Before we go into this, let me see. Okay, I think I'm rather on time. Before we can go to the issue of identification, let me focus a bit on sensitivity analysis. So, what I would say the wrong way to proceed with the ABM is try to put everything in a lot, bring in a lot of parameters, then you get something out of that, and you really don't know how you can obtain that. Okay, so many parameters, the role of some of even most of the parameters in producing your output is not entirely clear. Okay, so in order to rule out, so to get rid of the parameters that are not relevant for the kind of data that you want to generate, you need to rely on sensitivity analysis. What is the additional difficulty hurdle in this in doing sensitivity analysis with the ABM is that typically the metamodels are, since the ABM are expected to have nonlinear behavior, so also the metamodels are expected to be nonlinear. In fact, the previous example was of metamodel that I gave to you was a second order polynomial expression. So it was a nonlinear regression. So in these cases, computing the marginal effect of single regressors, if a statistical model is nonlinear, is in general not straightforward, because the impact of a single variable depends also on the values of the other variables. So, since global sensitivity analysis is a way to overcome this problem, so to apportion the uncertainty in the output to each of its inputs. Okay, so this approach is global in the sense that it's multivariate. It takes into account the joint distribution of all the parameters, and it also model free, which means that it does not rely on the model being linear. Okay, so we can always decompose the variance of the moment in an additive way in this way. So VI is the impact, the component of variance, which is obtained by letting the single parameter theta I vary, while we take the average on all the other parameters. So this, in a linear model, this VI would be the only term and would be equal to the square of the regression coefficient of theta I. Okay, so if the model is nonlinear, you have also these additional terms, which study what is the contribution of the variance to the total variance coming also from the couple of parameters I and j, but then also from all the triplets and all the combination of k parameters. Okay, so some good statisticians have come with a clever way to estimate, in particular, this STI, which is we could call inclusive variance. We can call it gross variance, which is basically the sum of all the terms in this decomposition that include the specific parameters I. So, for instance, VI plus VIG plus VIGM, and so on and so forth. All the terms that include a specific parameter I, and this is weighted over total variance. So this gives us, let's say, the gross impact of the parameter I into the overall variance, okay, of the moment. And from this total gross effect, we can subtract out SI, where SI is VI over the total variance, which is the let's say, first order effect, linear effect of the parameter I. So this difference is the impact of I, which depends also on the values of other parameters. So this method provides us with the estimate of the interaction component of each parameter. Okay, so what we obtain in some example is something like this. So in this case, this is straightforward. So we see that all the variance or in the average growth rate of the industrial production in our model depends on the parameter mu, which is basically the markup. Okay, so this is very trivial. This is a more interesting example. So you have the average number of bankruptcies, okay, in a simulation, and you see that here all the three parameters matter. So RCB is the policy parameter, and delta is basically the credit markup applied by banks. And so we see that the firm markup and the policy rate are the most important parameters to determine the number of bankruptcies among firms. But also we see that we have some interaction effects. So the interaction effect is the lighter part, okay, of the total effect of each parameter, while the dark part is the equivalent of VI in the previous slide. So I'm just done, and let me say just a couple of words about identification, which of course is very important in a frequentist framework, because a frequentist framework is all about finding the optimized values of the parameters which minimize or maximize a given criteria function and are themselves a function of some empirical moment and some simulated moments. Okay, so all this machinery here depends on the fact that F is well behaved, that is, that F has a global minimum. Otherwise, the results that you obtain are completely worthless. So you should take care of proving, of showing that your parameters are identified in order to think that you have achieved something in a frequentist framework. And so how do you do that? It's again a good thing way to find that your parameter is identified is to analyze the behavior of F depending on the simulations that you can perform, which depend on theta and on a random number generator. Okay, so you can do this from this. So you can simulate F, which is here called as G, on a high number of data points to show that in fact the function has a nice curvature, so your parameters are identified. In this kind of extensive computation, metamodels can be again useful, because you can, in this example, for instance, we use, instead of actual simulation, the metamodel predictions to draw the shape of G. So this also is again provides some computation savings in computation. So let me just conclude with quick summary of my talk. So calibration in the first sense, so constraining the model, not tweaking the model, is good, but so estimation must be always preferred to tweaking. So calibration in the second sense. Optimization of computation is always important in my view. It's true that you might happen to have high computational resources, like you might have a supercomputer like you have in COBE, but it's also true that, it's very easy to get to the boundary of computational resources for any given level of computational resources, because the task that we have as social scientists is enormously complex. So in my view, it's always worthwhile to optimize as much as you can. Okay, then if you have a larger computational hand, you will be able to do more. So this is why I'm stressing about the optimal design of experiments, and also on metamodels. And finally, try to have good models. And also, in order to have a good estimation, you have to build good models in the first place. So you need to run diagnostics with the help of sensitivity analysis already in the process of coding, with having in mind your research question, the kind of data that you have at hand that can be used to verify your research question, and try to keep your model simple and as effective as possible. And that's it. Thank you very much.